Okay. Welcome, everyone. Please allow me to introduce Professor Andrew Mason. Professor Mason received the Bachelor of Science in Physics with highest distinction from Western Kentucky University in 1991. Bachelor of Science in Electrical Engineering was honor from Georgia Institute of Technology in 1992. Master and PhD degrees in Electrical Engineering from the University of Michigan Ann Arbor in 1994 and 2000, respectively. From 1999 to 2001, he was an assistant professor at the University of Kentucky. In 2001, he joined the Department of Electrical and Computer Engineering at Michigan State University, where he is currently a professor. Dr. Mason is a senior member of IEEE and serves on sensory systems and biocast committees of the IEEE Circuits and Systems Society. He is an associate editor for IEEE Transaction Biomedical Circuits and Systems. Dr. Mason regularly serves on the technical and review committees for several IEEE conferences. He was co-general chair of the 2011 IEEE Biomedical Circuits and System Conferences. He is a recipient of the 2006 Michigan State University Teaching Scholar Award and the 2010 Withrow Award for Teaching Excellence. Please join me in welcoming Dr. Mason. Welcome, Dr. Mason.
Thank you. Thank you very much. I think all that means is that I'm getting old. So I will share a screen and present some slides here. So thank you guys very much for the invitation. I'm always delighted to talk about the work we're doing. This talk is part of the CAS Society Distinguished Lecturer Series, and it is titled Augmented Perception, Next Generation Wearables and Human-Machine Interfaces. This is work done in my research lab called the Human Augmentation or HAT Lab. And I usually start these presentations by showing where I am. We get a chance to do these international presentations, but we're just down the road from you guys. So I assume everybody knows how to get to Michigan. And I think it's about 4.5 hour drive away. So I've been fortunate enough to visit Toronto often. Sorry I couldn't visit you in person this time, but maybe again sometime later. I want to start by defining this, what I hope is a somewhat provocative topic of augmented perception. Well, augmented, or the concept of human augmentation, just means the use of tools to achieve more than humans naturally can. Now, I'm a lecturer or instructor by profession, so I tend to like to interact with my audience. I'm not sure how well we'll do in this platform, but let's give it a try at least. Since we have a small group of attendees right now, I would encourage people to, I'm going to have a few places where I will ask for some inputs. If you're so willing to turn on a microphone and just give me your thoughts. What do you think of when you think of a tool or technology for human augmentation? Anybody care to guess? Well, one of the most common responses we get is the cell phone, and certainly a cell phone is a ubiquitous tool that we all use now to augment our everyday life, meaning we enable it or we utilize it to achieve more than we normally can, communicate across vast distances that we can't naturally do, for example. So in engineering terms, all these augmentations would be considered examples of inputs, sensing, or outputs actuation. Now, the term perception in the title Augmented Perception just refers to the human ability to become aware of something. So it's the initial stage of awareness is perception. And from a psychology point of view, there are differences. Perception is just that observation of something, and awareness is when you become consciously knowledgeable of this. My lab actually recently, we rebranded ourselves, changed our name to the HAT Lab, or Human Augmentation Technologies. And this all got started by asking ourselves a question, a little more philosophical, sort of, what does it mean to know something? And, knowledge just means that the information is readily available to you without any effort, so you can act on it immediately. And then, why don't I know more? And specifically, since my lab group has historically developed sensing technologies, why don't I know, in that true sense of knowing, meaning I'm ready to act on it immediately, everything that all my technology and all my devices can know? What's stopping me? What's the bottleneck from me having that augmented awareness? So we all know facts, of course. We know our language and we know lots of math facts and experiences like when you were born and the things we can see, like what color the sky is. But there's a lot of things we don't know about our immediate situation or our current environments around us. So let's step forward on that interactive one there. But although we know many things, like the fact that there are lights on in my room right now, and I know that I'm wearing clothes, and I could tell if I were an audience sitting in a normal lecture hall, if there were people sitting in front of me, there are things that we know that we could just close our eyes and immediately know them. But there's so many things that we don't know. Like if you were sitting in an auditorium, how many people were behind you? Exactly what time is it? What's the temperature outside? Is the person next to me sad, or are they about to fall asleep? That about to fall asleep part, something that's important for presenters to pay attention to often. So these are things, interestingly, that technology can assess. The temperature outside, for example, how many people are in the room. We have technology that can find these things, but why don't we know them immediately? Meaning, from an engineering point of view, what is the bottleneck in allowing me to know all these things that my devices can assess? So, and this led to what we call our aha moment that I'll explain now. So the aha moment really, the phrase aha in English is an exclamation, that is often associated with this moment of discovery or the finding out of something new. So in our case, the aha moment is this concept that technology could enable superhuman perception, and that would enable us to know more things. It could, and in some cases it can, but there's still so much more it could do. And we wanted to look into what is the bottleneck in this. So this led to our project we've titled the Augmented Human Awareness, or AHA project, with a goal to establish technology for superhuman perception and just greater human knowing. So how does this human augmentation work? Well, let's imagine that there's a human, and we represent everything in this animation here as everything a human could possibly know as just being this globe, this earth. Well, we know that our bodies give us the ability to sense certain things. So through the use of our natural human senses, our eyes and our ears, we can detect a good portion of the things that are out there to possibly know. So we have some perception of things that are out there. We also know that we can build machines that have the ability to perceive a lot of things also, and many things that we can sense also, but many new things that we can't sense. So the idea of human augmentation is to be able to take those things that technology can sense that we can't, and then augment our knowledge by presenting that information back to us, sort of, feeding back that information that the machine can sense that we can't. That's the general concept of human augmentation. At this point, I'd like to bring up an observation that everything that comes into the human's brain has to go through the sensory network. And with the exception of some very invasive surgical techniques, all of the information that gets into our brain comes through our senses. So if we want to create some pathway for machine feedback to augment our understanding, we have to find a way to co-opt the existing human senses. All right, and when we do that, then we're actually taking the machine information and processing it. We're getting it into our brains, but going through our natural senses. And we define this as the machine to human feedback pathway. All right? And by doing that, it enables us to have superhuman or augmented perception. We can know more things than we would without. Right, at this time, I'd like to do a show you a short video that just gives some example of what we're talking about. So in this video, we have a student who's been sensory deprived. He's got noise cancellation headphones on and a mask, so he can't see or hear. And we've outfitted him with an electronic sensor set that we call a smart badge that's worn around his chest, and a set of a tactile stimulations on his wrist. So everything he sees and hears will be actually interpreted through tactile stimulations because he can't naturally, in this example, see or hear. So please let me know if this doesn't work out, but I'm going to jump out of the presentation and start this video. There's no audio, or there's no necessary audio here. So, all right. Does it look like this is being shown?
Yes, we can see it.
Okay, then I'll start from here. This is the demonstration. So these bullets will highlight what's going on. The student in the maroon sweater here has this tactile array on his wrist. He's holding a flashlight that will be used to indicate when he knows the lights have been turned off, so he has to use a flashlight. So there, the lights go off. He can't see that, but his tactile stimulation is telling him this occurred. When someone approaches him, he knows to hold up his hand. So again, his badge is telling him that someone is coming close. When he hears someone talking, he waves the flag just to know that he knows someone's talking, even though he can't actually hear them. And then we repeat the lights on and off to show that he's getting this different stimulus and able to respond to it. Okay, pretty simple. Let me get back to my presentation. Oh, should go away. Okay, so with that in mind, that early demonstration, which is of course just dealing with visual and sound inputs that we naturally could perceive unless we had some blockage of that. Now I want to point out some of the research goals that we're currently focused on. We're particularly interested in how we would be able to sense, like with sensors, with mechanical devices, and wearable devices, especially how we can sense stuff, especially how we can get perception of human social interactions. So beyond just the lights and talking in a room, how can we get information about what's going on during social interactions? How can the machine get that information and then augment my perception of these social interactions? And another element of this is, once I've got this information, what's the best way to get that back to the human in a way that will not be obtrusive, will be discreet, won't interrupt what I'm doing, and allow me to get that information back quickly and in real time. And also a big concern is that we want to avoid any congestion of our audio and visual channels that we tend to be engaged in pretty heavily all the time. And for this, we're going to talk about some of the work we're doing in tactile communication pathways. Oh. Okay, so now I'll turn on to the next stages of the talk, which are 3 different topics we're going to cover. One is the behavior monitoring of social interactions, a little bit about human behaviors and their monitoring, and try to answer the question, or look into the question, can machine augmentation be used to improve social interactions? And now in this sort of appropriate for our COVID era of virtual meetings and virtual seminars like this, we're interested in looking at virtual interactions and how human social awareness becomes limited in these virtual actions, and how machine augmentation can be used to improve them. And then lastly, I want to talk a little bit about the machine to human communication pathways we're establishing using a tactile stimulation, and ultimately try to answer the question, can humans receive information, receive data messages via tactile inputs? Give me 1 second. Okay. So the first work is on behavioral monitoring, is largely done by one of my grad students, Silmarie de Villa Montero. First, we note that social interactions are not just about having fun and hanging out with our friends. They actually have a really significant impact on our health. They do affect our physical and our mental health, and reducing the quality and quantity of social interactions has an associated increased risk of depression and cardiovascular disease. So if we can find some way to improve social interactions, we think it can have a positive impact on health overall. However, social interactions are very complex. They involve a combination of personal things, what we call personal factors that are internal to each individual and unique to each individual. And then when we start sharing, we have the environment that we're in that plays an issue. Of course, the the communication between us, some of it verbal, but there's a lot of nonverbal. Just consider that humans as a species were communicating nonverbally many, many years, or thousands and tens of thousands of years before they were communicating verbally. So humans inherently utilize a wide range of nonverbal communication. The personal factors include things like your emotions, your very short-term emotions, your longer-term moods and attitudes, and ultimately your personality traits. And this is what make each of us individual and unique, and also part of what makes it challenging to do monitoring of social interactions. We also engage in, and we're particularly interested in, these non-verbal communications that occur between humans. Things associated with our eye movement or the gaze direction, who we're looking at, body movements, facial expressions, and a variety of other things that are exhibited in our nonverbal communication. In addition, we want to pay particular interest to some unconscious behaviors that can negatively impact our social behaviors. So these unconscious or implicit biases are often occur in the workplace. So the nature of these undesirable behaviors and these unconscious behaviors is that they are contributed to by our emotions, our intentions, and just what we end up communicating. However, in these communications, especially for these implicit biases, we are very poor at self-analyzing. So our self-awareness is very limited. So we're hoping that we can establish mechanisms by which the machine can come in and provide an analytical understanding that can aid people in dealing with their unconscious biases. And ultimately toward a goal, though, of improving social interactions. So this is a little cartoon of how this idea works. So particularly imagine a work setting where people are standing around communicating, maybe trying to solve some task. So we'll just call this a social interaction. And if we could implement inside the social interaction monitoring technology through wearables, for example, then we could capture some human behavior data. This data would then be fed into algorithms that would be designed to process and extract the behavioral information that would be valuable to then present as feedback. So these are some illustrations. Let me bring up the key. What this represents is a different way, a model of visualizing what's going on in this team, where each of these circles represents one of the individuals, by looking at things like the conversation density. So we imagine that this diamond in the middle would move toward wherever whoever's speaking the most and taking the most of the conversation. We can also use this data to establish who's paying attention to whom. And these pink lines of various levels of dashed and dotted can represent this concept of how much mutual attention is occurring between any dyadic pairs. And we can also look at the individual's emotional level. So arousal is just your, like how excited you are by something is one of the easier parameters to measure. So we could get a gauge of that. So this combination of information about emotional arousal, attention, and conversation can be very illuminating about a group interaction. And then we feed this information back to the individuals so they can all have augmented awareness of the interaction in real time. So when we have an in-person interaction, what are the things we look for in order to better understand what's going on during those interactions? So as some examples, to get a sense of how much attention someone is paying to you, you would normally rely on the visual contact. Or to get a sense of how much, we could also, in order to get that same sense, you may also rely on verbal feedback. What's very common in social interactions are people responding with uh-huhs and yeahs and just something to let you know that they're attentive. And to get a sense of emotional state, we rely on the intonations or the pauses and delays that they use when they're talking, for example. We can also, to get the emotional state, we can rely on our view of facial expressions. So, and to determine who's a group leader, we would often look at who's talking the most or what sort of intonations are being offered by those who are in authority. So can a machine capture these social elements? And the answer is yes, we certainly can. Many of these we can capture just with simple microphones and cameras. So if we look at the broad scope of monitoring these social interactions, we see that we can look at the two different aspects, the sensing and then the extracting of information through algorithms. So here for extracting these biometric information, the cameras and microphones we mentioned, but we're also really interested in looking at a variety of physiological sensors, things that can measure, for example, my heart rate or heart rate variation, because they're very strong indicators specifically of emotion. And algorithms, of course, there's all kinds of signal processing and feature extraction and ultimately classification that have to be involved in this process. In addition to these physiological parameters, there are a lot of nonverbal messages that as we talked about previously, including things like the talk time. So clearly, if someone's not speaking and not utilizing much of the conversation, then they have a different level of engagement that we would like to be able to analyze. So these sensors and algorithms can come together to form a wearable solution for monitoring social interactions. Now, here's some existing systems that have been out here to measure social behaviors. I won't go through details on them, but just to show that there are within the research community, and much of this by the CAS research community, a significant effort at wearables, particularly to monitor physiology, but a lot of these things directly for social interactions and emotions. Things like EEG can be utilized to extract a lot of interesting parameters for emotions. And one of the things we really want to do with these is get some group level feedback. So looking at things like conversation dynamics, the way that it varies in groups of people talking, because it's useful for us in assessing collaboration and the performance of teamwork. We can also get individual information, things like your emotional state and interactions in social environments. However, monitoring technologies face a variety of technical challenges that need to be overcome before we'll truly have the ultimate smart social monitors. And some of these are related to the pre-processing of the signal. So we extract data from using the sensors, and then we have to go through a series of signal processing steps. One of the real challenges is just getting the different timestamps coming from different sensors that are sampled at different frequencies, and then aligning these times so that we know when data from different sensors can be associated with the same social events that we're trying to tie them to. So that time sequencing and dealing with different formats and sampling rates becomes quite a challenge. We also have to deal with the normalization across different individuals and multiple sensors spread throughout an environment, collecting data. How do you get those calibrated to some same standard? And dealing with noise issues from the environment or from the hardware itself. And then in processing this data, we're left with face a trade-off between whether you want to use subject-dependent models or subject-independent models. So if you have a subject-dependent model, that means that it relies on some knowledge of the individual. We can definitely improve the accuracy. However, if we can abstract outside of some individuals and make it independent of the subject, then we can process the data much more quickly. So there are definitely trade-offs that have to be encountered in this. And then finally, there's a lot of concerns associated with developing of training data sets. So a lot of work done in research labs like mine are done in laboratory conditions. But real life scenarios offer much more dynamic responses and need to be more thoroughly considered. There's also in our DEI, or diversity, equity, and inclusion awareness, a need to look at how data is collected and who it's collected from, and try to remove bias from our training data sets so that our algorithms will not be spreading some bias. Okay, that's just a little introduction to the concept of social monitoring. Now I want to talk about a separate issue, which is still related to behavior monitoring, but in virtual or distance collaboration. Now, as I'm sure all of you, like me, working from a home environment now due to the COVID-19 pandemic, we're all learning a lot more about working through virtual interactions. And there's certainly some advantages and some disadvantages. The challenges of virtual meetings are that we are now disconnected from each other. We sit in meetings looking at black boxes now, or maybe sometimes there's some faces, but we're certainly, our level of engagement, personal engagement, has been significantly reduced. And this affects our ability to establish rapport with the people that we're meeting with. Of course, there are advantages to virtual meetings. It enables us to practice social distancing, and it cuts down on our carbon footprint, so we're protecting the environment. And it's taught us new techniques that we can apply even after this pandemic ends, such as we can eliminate a lot of our driving using virtual meetings. This will improve our work efficiency in the sense that we spend less time in the car and more time in front of the computer or whatever your work is, and can continue to keep our pollution load down. So because these virtual environments appear to be with us for life now, we wanted to take a look at how we could utilize technology to improve the same thing, our understanding of human interactions, but in a virtual environment. But one of the challenges is that some of the hardware we talked about earlier, like physiological monitoring, it won't really be accessible. If we're just me sitting in front of a computer, I don't readily have an EEG and different forms of physiological monitors mounted onto my body. So what can we do with the limited things we have available? Every virtual meeting has a microphone and a camera. and a high performance computer, and at least your personal computer or laptop, to do a lot of processing. So can we utilize these things to give us some insight into human behavior beyond our natural human senses? So in many cases, we find that we can use the capabilities of a camera to monitor a wide range of human behavior features, such as movement of my body, the orientation, whether I'm engaged with the group in front of my monitor, your posture. You can even get breathing and heart rate from cameras. Of course, we can find facial expressions, smiles and frowns, and one of the most important elements, eye gaze. So knowing who is looking at whom is one of the most important qualities in establishing an understanding of human social interaction. So we've looked more into what can be done with cameras and different frameworks for video analysis. Though falling under the concept of nonverbal communication, we can look at things like nodding, orientation, just where you're facing, and facial gestures. So we have explored this open software called OpenFace that extracts a variety of, it can track gaze for sure. So we can say, for example, who in a Zoom meeting like this, who is looking at whom. We can also identify things like if someone is disgusted by a remark and they roll their eyes, you can identify those things pretty readily. We can also extract what are called action units, and these are by looking at different muscles in the face. Each of those becomes an action unit, and they can be combined together to tell us more about emotions. So, for example, combining action units, we can give some information about happiness, sadness, surprise, and a variety of others, as there's a little table there. But let me play a quick video here that is an example of how we can use OpenFace to extract the affect, mood, attention, and engagement from these combinations of things. So this, why aren't you playing? Okay. Well, I won't, in the interest of time, I won't belabor this. It worked just a moment ago when I was testing it, but you can imagine that this is the OpenFace software extracting things about the person, and as they smile and frown, you get different results back, and you can track their eye gaze, and pretty common parameters for monitoring faces. But we believe that this information has a great potential for finding things like emotional expression, different personality factors, and ultimately be informative for social interactions, all just using cameras. So there's also some recent work that has shown even more potential, more than just the physical movement of the head and where your eyes are looking. We can also extract heart rate and respiration rate. So, this example shows, just looking at these, sinus cavities, we're able to look at the signals that can interpret heart rate from this. And there's another example using cell phone cameras to measure respiration rate by chest breathing in and out. And there have been publications on using the rear camera of a cell phone as a PPG monitor for heart rate monitoring. So there's a lot of interesting things that can be done with the existing cameras. And while significant work has been made toward all of these individual parameters, one of the problems that we have left is that there's not been a lot of work done in analyzing the dynamics of group interactions during virtual collaborations. So there's still some interesting work to be done there, and we continue to explore how we can analyze group interactions using the cameras and microphones in our virtual meetings space. All right, then lastly, I want to turn back to this, the feedback pathway. So bringing data back into the humans. It's all well and good that we can develop sensors to identify things, but how do I reach that level that I started the discussion about? How do I know it? How do you get it back to the humans? Well, there are, this is, as I said before, information can't just absorb into our brain, as we often joke about when we were in school, and we like to go to sleep with our textbook and hope that it will soak into our brain, right? The only way in is through our senses. So there are two major pathways, let's go say the non-invasive pathways. These are the ones using our senses. There are also, of course, invasive methods that we can crack open someone's skull and we can put probes into it and we can stimulate, or we can slice open other parts of the body and wrap electrodes around nerves and inject information that way. Well, let's say that none of us probably wants to have our skulls cracked open or our nerves pulled out. So we're really interested in looking at the non-invasive methods and how we can utilize them to as a pathway. This goes into a little more detail about the whole cognitive process. So we can just pay attention to the graphic at the bottom, and it kind of walks through, all incoming information comes through our senses. And then it runs through essentially like a attention multiplexer. So we cognitively decide what elements of our input senses we want to pay attention to. And then that we choose to pay attention to or focus on is what will get processed in our brain, be stored in our local term memory, and then ultimately we get to decide which of those things we want to store in long-term memory. The important element we want to point out here is the fact that the attention becomes really critical, because we only have the ability to pay attention to a certain number of things. So when we're talking about people with busy lives already, we have to be very careful when we want to give more information. If we want to know everything automatically, how do we make that happen? So in this talk, we're going to focus on the concept of electrotactile as an alternative form of communication. So to get started, let's imagine that we're looking at this light. We want to know if it's on or off. And we can represent from an engineering point of view that this information just has one bit, it's on or off. However, when we are using our eyes to engage and to make this decision, we're actually running a lot of information to like 10 megabits per second through our brain just to collect this one piece of information. So if we were to try to use a machine, let's say I needed to monitor a lot of lights and it was very taxing on me visually, it's important to note that if we wanted to do this with the machine instead, we really wouldn't want to have this information fed back to us through a visual pathway. In fact, in many of our jobs, sorry, I got a little bit ahead of myself though. So although audio and visual feedback pathways are the most common methods of feedback, our Fitbits and our alarms or notifications on our cell phones all come to us as audio or visual signals. This is not really the best method for multitasking, because our eyes and ears are already engaged in whatever activity we're working on. So this can lead to an attention span challenge. So we want to look for an alternative pathway. And this leads to the concept of tactile. So tactile sensors in the skin can be used to transfer information. The Braille language, for example, is widely used, what's called sensory substitution for visual reading. We use our fingertips to do the reading. And this shows us that the nerve endings in our skin can be used for unobtrusive communication that doesn't interfere with our eyes, sight, and hearing. It's also interesting to note that we have a tremendous amount of tactile receptors. And in fact, the skin is the largest sensory organ in the human body, and it is largely underutilized except for a few key things like our fingertips and our tongue. So some of the examples of tactile feedback systems that are out there include this haptic belt that has a set of vibrators built around the waist, And then sensory information collected on body-worn devices can be used to buzz these vibrators and communicate different information. There's also examples of like tongue stimulators and many different finger stimulators that are out there. And these use different, well, yeah, I want to talk now about the different modes of tactile stimulation. So we can identify here the possible modes include the vibration, which is just like the buzzer or the vibration in your cell phone that goes off in your pocket to let you know that a call is coming in. There's also mechanical, like the previous example of the fingertip sensor. It uses pressure, mechanical pressure to actuate the skin, and then we receive that as a signal. And we can also do electrotactile, where we just inject electric currents into the skin. If we go into the slightly invasive techniques, there are cuff electrodes that get wrapped around the nerves. There are a couple different forms of these sort of nerve intervening types of tactile stimulators. I want to put it forth an idea that these electrotactile has some really great advantages. So not only does electrotactile allow us to overcome these visual and audio limits, but it is a great, has a high density pathway for us to get information back. Also, there's been studies that show that tactile inputs are less obtrusive and distracting to us than additional audio and visual information. So among all of these non-invasive pathways to the brain, tactile stimulation really emerges as a great candidate for producing, adding additional information to our daily lives. And in particular, electrotactile has some great advantages. Let me just quickly explain what electrotactile stimulation is. It's not a completely novel concept, but there are some novel elements of it. You put an electrode on the skin, as shown in this illustration over here. This will pass an ionic current between electrodes, and when this creates a potential buildup along a nerve, it will cause an action potential to fire. So then by putting different waveforms on the electrodes, we can produce a pattern of stimulations, or excuse me, of action potentials running along the nerve that your brain will then interpret. Everything we've been able to do so far, it feels like a vibration, but of course there's not actually a vibration occurring. We're just injecting currents in a way that lets you feel like there's something walking along your skin or tapping on you or vibrating on your skin. But this information then flows into our brain, and we can sense it as, oh, there's something going on my skin that is not a normal process. But by varying the signals coming in, we can then create almost like a tactile language that will allow us to get some high bandwidth communication through these tactile inputs. I think I actually talked through all of these issues on the last slide. I will point out that there's in difference to this concept of haptics are generally referred to the idea of taking things that you would feel as touch and then reproducing them. For example, a mechanical glove is used in a remote surgery to touch and feel something, and then the doctor in a different location wears a glove that reproduces the sensations of that touch on his own hand. In contrast, electrotactile can be used to just put in any information. For example, like Braille, you're reading a novel or a newspaper coming through your fingertips. Its data can be open-ended. So electrotactile can be used in the same way. So we think it can be a very interesting pathway for wide open communications. This all has to come in through the brain, through the somatosensory cortex, and one of the very interesting things that is yet to be explored is what happens when we start loading that part of our brain with more information than it's used to processing. And only some additional research will tell us what we can do with that. So in conclusion, I'd like to point out that I think that there are some very interesting challenges and great potential in these three areas. In sensing modalities, the things that will allow us to find health and physiological parameters and monitoring environment for safety and different human social interactions and behaviors. And then we need to deal with the signal processing challenges and new machine learning algorithms that will help us fuse together information from a lot of different sensors that them individually can't tell us much, but together might be able to extract a lot of great information. We also get challenges related to edge computing and real-time computing. We want these things to be done on our body-worn devices. Ultimately may lead to a new area of psycho or neuroengineering utilizing these types of sensors. And then lastly, we have to pay a lot of attention to this concept of the machine to human feedback pathways. How do we get information coming back to us in high bandwidth without using our eyes or ears in a manner that can be unobtrusive, doesn't stop us from doing the things we are already trying to do, that's not disruptive, not discrete, and allows a robust and signal so that we really know what the information is we're getting back. All right, with that, I will call this to a close. Thank you guys very much for inviting me to give this presentation. And thanks to the 3 students who contributed directly to this project.
Thank you, Professor Mason, for this spectacular and crystal clear lecture. We appreciate it so much. So everyone, please, if you have any questions, you are welcome to jump in. You can write in chat or you can unmute yourselves if you would like to ask any question. Okay, all right. I think this concludes our distinguished lecture today. We were very pleased to have you, Professor Mason, today. The record link will be sent to all participants via email. And please, if you have any further concerns, let us know. Thank you so much.
Thank you.